is Mr. Potter. What we're going to talk about in today's lesson is we're going to discuss arithmetic and geometric sequences. And this should be a review for pre-cal, but we're going to try and connect it to the limit ideas that we've just been talking about in the remainder of Chapter 8. Now, I'm doing this section slightly out of order here because I think that section 8.1 really goes well with the Chapter 9 material, and I also think that section 8.1 makes a lot more sense if we look at it after we've talked about these limits at infinity, after we've really understood what's going on here. So I'm going to start with a quick recap of what we mean when we're talking about an arithmetic sequence. The idea behind an arithmetic sequence is that we're going to have some first term and then a second term which is d off of it, and then the next term is 2d away from my original term. And so essentially what's happening is to get to every successive term in the sequence, I get to it by adding d. I'm adding a common difference. And so this common difference is what we're trying to deal with. Now, when I look at arithmetic series, when I look at arithmetic sequences, there's two ways that I can look at this. One way I can look at this is as a recursive formula. In other words, let's say that I have some sequence where I tell you that the first sequence, the first element of this sequence is 6, but every other element is going to be 3 more than the element that came before it. So in other words, a sub n is really equal to 3 plus a sub n minus 1. So I could figure out this sequence by saying the first element has to be 6. The next element has to be 3 more than that, which would be 9. The next element would be 3 more than that, which is 12, and so forth. So every time to get the next element in the sequence, I add 3 to the previous element of the sequence. But another way that we can look at this is we could look at this in what we call an explicit formula. In other words, I can actually give you a formula for a n, so I can determine any element of this sequence just by knowing what a1 is and what n is. And I'm noticing that because this is my common difference. Remember, this is a plus n, this is a plus 2n, this is a plus 3n. A is what we started off with. So this is really 6 plus, and I'm doing here 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, and 3, 6, and 9 have respectively been added to 6 to get these 9, 12s, and 15s. So this is really 6 plus 3n. And so what I've got here is I've got an explicit formula for this sequence that we've already talked about recursively. So whenever I'm looking at an arithmetic sequence, there's two ways that I can define it. I can define it recursively by giving it an initial term and giving what happens to get to the next term in the sequence, or I can give it explicitly. In other words, I can give it almost like a formula. I mean, I can almost think of this as a of n being 6 plus 3n. And so there's these two ways that I can look at this, and I can talk about it anytime that I'm adding a common difference, even if it doesn't look like I'm adding the same thing every day. So let's say I'm looking at this sequence. I've got the natural log of 2, the natural log of 4, the natural log of 8, the natural log of 16, the natural log of 32, and so forth. So if I'm looking at this sequence of numbers, it certainly looks like instead of adding, I'm multiplying. But in reality, if I wanted to find the difference from here to here, this difference would be the natural log of 4 minus the natural log of 2. And this distance here would be the natural log of 8 minus the natural log of 4. And this common difference would be the natural log of 16 minus the natural log of 8. Well, when I subtract logarithms, I really end up dividing their arguments. I get the natural log of 4 divided by 2, the natural log of 8 divided by 4, the natural log of 16 divided by 8. Well, these are all the natural log of 2. And so I can think of this in a couple of ways. Again, if I wanted to think of this from the recursive standpoint, I could think of this as my first term being the natural log of 2, but every other term really being whatever my previous term is plus the natural log of 2. Because if I add the natural log of 2 to the natural log of 2, I get the natural log of 4. And if I add the natural log of 2, adding means I multiply the arguments, and I get the natural log of 8. And if I add the natural log of 2 to this element, I multiply the arguments, and I get natural log of 16. So I can think of this from a recursive standpoint, or I can think of this of an explicit standpoint. So I can think of this where my formula a sub n is really going to be my first term, natural log of 2, plus n times my common difference, which is the natural log of 2. In other words, the same way we thought about it here, except now the property of logarithms comes into play. And if I have a coefficient in front of a logarithm, it really becomes the exponent of the argument of that logarithm. And so what I actually end up with is the natural log of 2 to the n plus 1 power. So arithmetic sequences can actually take a lot of different forms, not just simply adding the same number. I could deal with this with fractions, or I can deal with this with decimals. I could deal with this with logarithms. There are lots of different ways that I can look at arithmetic sequences. So that's a review, as is talking about geometric sequences. So remember, the difference here with geometric sequences is that once I know a term, the next term of the sequence is going to be that term times r. The next term of that sequence is going to be that term times r again. So this is really times r squared, r cubed, r to the fourth, and so forth. And again, just as we talked about before, I can talk about this recursively, where my a1 is going to be some value, but each a sub n is going to be r times a sub n minus 1. Or I can talk about this explicitly, where a sub n is going to be equal to a times r to the n power. So I've got these two formulas that are perfectly both legitimate. And sometimes it's easier to think of these things in terms of the recursive definition. Sometimes it's easier to think of them in terms of their explicit definition. Let's go through a couple of examples of this. So let's say that I start off with an example of this sequence. I've got the sequence that goes 3, 6, 12, 24, 48, etc. So I've got this sequence, and it's pretty clear what my first term of the sequence is. A1 is 3. And it's also clear how I'm getting to the next term of the sequence. I'm multiplying by 2. So my common ratio in this case would be 2. And so I can talk about this from a recursive standpoint. This would really be A1 equals 3, and A sub n is equal to 2 times A sub n minus 1. Or I could think of this from the explicit standpoint, where A sub n is really 3 times 2 to the n power. So that's one way that I can look at this. But we don't always think of this in terms of whole numbers. As a matter of fact, we often see this in terms of rational numbers. So let's say, for example, I have this sequence where I'm starting off with 18, then I get 12, then I've got 8, then I've got 16 thirds, and then this continues on and on. So the question is, how am I getting from one term to the next term? Well, I know that this is supposed to be my A term, my initial value, and this is supposed to be A sub r. This is supposed to be A sub r squared. So, in other words, to get from here to here, I'm multiplying by r. So, in other words, if I take a look at 12 over 18, that should be equal to r. And similarly, to get from here to here, I'm multiplying by r. So 8 over 12 should also be equal to r. And I can easily reduce both of these fractions and get that 2/3 ratio out of it. So what's happening here is that my initial term is 18. My common ratio is 2/3. And so I can again talk about this recursively or explicitly. I can either say it's 18 times 2/3 to the nth power, or I can say that this is equal to 18, or excuse me, where A1 is 18 and A sub n is 2/3 of A sub n minus 1. So again, we can look at both of these arithmetic and geometric sequences either by looking at them from a recursive standpoint or looking at them from an explicit standpoint. Now, what's often more interesting is I will be given not a complete sequence, but I'll only be given certain parts of that sequence. So for example, I might be given an arithmetic sequence, and I might be told that the second term of my sequence is 6, and that the 6th term of this sequence is 30. And I need to find out about this sequence. Well, remember that this is the second term of the sequence. This is really my first term plus my common difference. And if this is the 6th term of my sequence, this is really my first term plus 5 of these common differences. And so that means that 4 of these common differences, the difference between these has to be the difference between these values, which is 24. And so I can determine my common differences 4. And so now I also know what my initial term has to how about a 6? That sounds like a better number. Let's try a 6 there. So if this common difference is 6, that means my first term had to have been 0. And so what's happening here is I can talk about this explicitly. The nth term is going to be 0 plus 6 times n. Or I can talk about this explicitly where my first term is 0 and recursively each term is the previous term plus 6. So we have this method of solving for a particular, if I'm given 2 elements of this sequence, I can determine both where my starting point is and where my common difference is. In essence, I'm solving a system of 2 equations with 2 variables, a and d. And I can do the same thing for a geometric sequence. Let's say that I told you that my a sub 2 was 27 and my a sub 7 was negative 1/9. So I can take a look at this and determine what my formula is going to have to be. Keep in mind, this is my second term of a geometric sequence. So this is really a times r, and this is really going to be a times r to the 6th to get the 7th term of a sequence. And to get from here to here, I'm really multiplying by r to the 5th. So in other words, a to the 7 divided by a sub 2 is going to be r to the 5th power, but this is also negative 1/9 divided by 27, or negative 1 over 243. And so I can determine that my common ratio by taking the 5th root of both sides gives me r equals negative 1/3. And if r is equal to negative 1/3, that means that this 27 had to be negative 1/3 times something, and that something is 81. So I found out what the first term of my sequence is. I found out what my common ratio is, and I can actually list out elements of this sequence if I wanted to, just by taking 81 and multiplying each time negative 81 and multiplying each time by negative 1/3. So that would give me 27, and then a negative 9, and a 3, and a negative 1, and a positive 1/3, and so forth. So I can actually solve for these common differences and common ratios because I am in essence solving a system of equations. Now, how do I type this into what we've been talking about, because what we have been talking about are limits. And I mentioned earlier that when we're talking about these explicit formulas, I can think of a sub n as really being a function a with an independent variable of n. And so I can talk about a sequence having a limit. So here's our definition of that. So we say that a sequence a sub n, and we usually put the a sub n between these curly braces to denote that it's a sequence. A sequence a sub n has a limit L as n increases without bounds if for every n greater than or equal to some capital N, there exists some epsilon greater than 0, such that the absolute value between every term for this n minus my L. In other words, the difference between my limit and any term in the sequence beyond some point is going to be less than that epsilon. What that means, if I was to look at a sequence like 1, 1/2, 1/3, 1/4, 1/5. This isn't geometric or arithmetic. But the thing is, there is some point where I could say, okay, I want to choose n as 100. That means that I could figure out some epsilon, say 1/100th, and every term has got to be within that limit by at least a window of 1/100th. In other words, these values get closer and closer and closer to a sequence, to a limit value. They actually get arbitrarily close. In other words, I could choose how close I want to be, and I could calculate what n has to be such that every point beyond has to satisfy that. Now, what we do is we actually say that the limit as n increases without bounds of my sequence a sub n is equal to L. And we also say that a sub n, the sequence, converges to L. So I want to go through a couple of examples of what we're talking about here. So let's say that I'm dealing with the sequence a sub n equals 2n minus 1 over n. So I want to start by taking a look at some of these elements. So my first element is going to happen what happens when I substitute n equals 1, which is going to give me 2 minus 1 over 1, which is 1. The second sequence is what I get when I substitute it 2. So I'm going to have 4 minus 1, which is 3 over 2. And so forth. So the third element is going to be 2 times 3, which is 6, minus 1, which is 5, over n, which is 3. And each term ends up having a larger numerator than it does a denominator. A5 in this case would be 9/5, and so forth. But what we can say is that these values are not increasing without bound. I'm going from 1 to a half, to 1.5, to 1 2/3, to 1.75. This is 1.8. They're increasing, but they're not increasing by very much. I could actually determine what a sub 1,000 is. A sub 1,000 is going to be 1,999 over 1,000. And it certainly looks like, although the numbers are pretty big, this is less than 2. And so what we actually find out is if we take the limit as n increases without bounds of my sequence, this is really the limit as n approaches infinity of 2n minus 1 over n. And this sequence looks an awful lot like a infinity over infinity indeterminate form. And so L'Hopital's rule is a wonderful way to approach this. So using L'Hopital's rule, I end up with the limit as n increases without bounds of the derivative 2 over the derivative 1. And so this ends up just being a limit of 2. And so I can use this idea of treating my function, my sequence, as if it were a function, and then treating this function using the rules for limits that we've developed so far as a way of approaching the limit of the sequence. So let's do one more like this. Let's say that my sequence a sub n is going to be n over n squared plus 1. And just as before, I want to take a look at some of these elements. So my first element when n equals 1 is 1/2. My second element when n equals 2 is going to be 2/5. My third element as n equals 3 is going to be 3/10. My fourth element ends up being 4 over 17. My fifth element ends up being 5 over 26, and so forth. And it certainly appears, at least to me, that the denominator is increasing at a faster rate than the numerator. Looking at this, if I had to ask if this was a top-heavy or bottom-heavy situation, I'd say it was a bottom-heavy situation. And so if I look at it from the limit as n increases without bound of n over n squared plus 1, I'm looking at this as a indeterminate form, infinity over infinity. And so L'Hopital's rule seems like a way to approach this. So the limit is n approaches infinity of 1 over 2n, and I know the parent function behavior as n increases without bounds, my function approaches 0. And so I can say that this sequence converges to 0, just as this green sequence converges to 2. And in fact, all of the rules that we had for any type of limits are going to apply to these limits of sequences as well. The idea that the sum of two limits is going to be the limit of the sum, the product of two limits is the limit of the product, and so forth. Everything that we talked about back in chapter 2 still applies. But there is one more limit that I want to talk about, because it's been a while since we've dealt with this particular limit. So I want to take a look at this sequence. A sub n equals the sine of n pi over n. Now this looks very complicated, but if I take a look at these terms, my first term is going to be the sine of pi, which is zero over 1. The sine of 2 pi is going to be 0 over 2. The sine of 3 pi is 0 over 3. Well, it certainly looks like the limit is 0. As a matter of fact, it looks like this sequence is a constant sequence. But I can prove that this limit has to exist. I can prove that the limit as n approaches infinity of sine n pi over n is equal to 0, because I remember my behavior of my sine function. I know that sine of theta always has to lie between -1 and 1. And that's certainly true for n pi. And because this is true, I can certainly think of -1 over n and 1 over n being boundaries for sine of n pi over n. So if I wanted to take a look at the limit as n increases without bounds of the sine of n pi over n, it certainly would lie between the limit as n increases without bounds of negative 1 over n and the limit as n increases without bounds of 1 over n. But both of these have very well-defined behavior. Both of these, we know their parent functions approach 0 as n increases without bounds. And so my limit can be, as a matter of fact, must be 0. And of course, we talked about the sandwich theorem. Back in chapter 2. So the sandwich theorem also still applies. So in other words, if I'm dealing with a tricky periodic function like sine or cosine, I can always bound it between its range and then use those range values to kind of pinch it between two limits that ideally would be the same. So notice that I've proven that this limit must in fact be equal to 0. So we will be dealing a lot with sequences in this chapter 9. In our next lesson, we're going to talk about some sequences that show up so often that we just have to memorize them. But that's a lesson for another time. This is Mr. Potter. Thank you for watching. Have a great day.